So, continuing on with our discussion of chapter 6, let's do another example where we balance a chemical equation given a word problem. So in this case, we're shown that aluminum metal reacts with a solution of hydrochloric acid to yield a solution of aluminum chloride and hydrogen gas. So aluminum metal will be Al solid. Hydrochloric acid has the formula HCl, aqueous. Aluminum chloride, so we have aluminum 3+ and Cl-. We cross our charges and that gives us AlCl3, aqueous. And then hydrogen gas has the formula of H2 gas. Now, one thing that I want everyone to pay attention to here is that in this equation, we have an isolated pure element of hydrogen, which means you should immediately think, okay, I can use half notation. So first I'm going to do a preliminary tally of the atoms of each element. So I have 1 aluminum, 1 hydrogen, 1 chlorine. I have 1 aluminum and 3 chlorines, and then I have 2 hydrogens. So first things first, I'm going to balance every element that I can without resorting to half notation. So in order to balance chlorine, 1 times what would give me 3 chlorines? What coefficient should I guess for hydrochloric acid? And let's try to get a few responses in the chat. 3, yep. So that in turn gives us 3 hydrogens and 3 chlorines. So now that I have chlorine balanced, I'm going to look at hydrogen. I'm going to guess 2 times what would give us 3 hydrogens? 2 times what fraction would give us 3 hydrogens? So we put what we want on top, what we have on the bottom, and that in turn gives us a fraction of 3/2. Perfect. So rewriting our preliminary balanced equation, we have aluminum solid plus hydrochloric acid aqueous leads to aluminum chloride. So we have 3 hydrochloric acid molecules leads to aluminum chloride plus 3/2 H2 gas. And now what we do is we multiply all of our coefficients by a common whole number. Now, what whole number should we pick in this case? Two, yep. That gets rid of all of our fractions, and we're left with the following completely balanced chemical equation. Perfect. Any questions on this example? Any questions on this example? If not, let's now work on the following example and try to balance the following chemical equation. So make sure you start off by writing valid formulas. So once we have that established, we'll discuss and we'll write out the correct chemical formulas for our reactants and products in about 3 minutes. And if you're feeling ambitious, you can try, once you have your formulas for your reactants and products, you can try to balance the chemical equation and message your responses in the chat. and we'll discuss the chemical formulas in about 2 minutes. And some of the balanced equations that I'm already seeing in the chat look perfect so far. So let's discuss our chemical formulas for each of our reactants and products. So zinc, it's an atomic metal, so just Zn solid. Phosphoric acid is derived from phosphate. So crossing our charges, we get H3PO4. Hydrogen gas is just H2 gas. Just for a personal note, we see a pure isolated element. We'll keep that in mind for later. And zinc phosphate, so we have zinc 2 plus and PO4 3 minus. We cross our charges and that gives us Zn3 PO4 2. And zinc phosphate is a solid. Though that's not super important for this problem. So now that we have our chemical formulas, let's take a moment and let's take about 2 to 3 minutes to try and balance the following chemical equation. And don't be shy to message your proposed balanced equation coefficients into the chat. And for the response I just received, the response I just received looked good so far. Just for the response, both of the responses I received, just make sure to double check that the coefficient for hydrogen is balanced, but they look good so far. And we'll discuss in about another minute and a half. Let's try to get a few more responses in the chat before we discuss. Okay, so let's now discuss this example. So first things first, let's count the atoms of each element. So we have one zinc atom. We have 3 hydrogens, 1 phosphorus, and 4 oxygen atoms. We have 2 hydrogen atoms in hydrogen gas. And in zinc phosphate, we have 3 zinc atoms. We have 2 phosphorus and 8 oxygen atoms. So we'll leave our isolated elements for last. And let's start by balancing an element that's found in a compound that is not balanced. So let's focus on phosphorus for now. We have 2 phosphorus atoms on the right. We need 2 on the left. So 1 times 2, 1 times what would give us 2 phosphorus atoms? 1 times what would give us 2 phosphorus atoms? What coefficient do we need for phosphoric acid? 2, yep. So we now have 6 hydrogens, 2 phosphorus atoms, and 8 oxygen atoms. Okay, so phosphorus and oxygen are balanced. Okay. Now the question becomes, if for zinc, we have 3 zinc atoms on the left, 1 times what would give us 3 zinc atoms on the right? What coefficient should we put in front of zinc? What times 1 would give us 3? What times 1 would give us 3?
3.
3, yep. Okay, perfect. Now we balance hydrogen. So we have 6 hydrogens on the left. 2 times what would give us 6 hydrogens? What coefficient do we need for hydrogen? 2 times what would give us 6? 3, yep. Perfect. So now we've balanced all of our elements. So let's write out now our balanced chemical equation. So we have 3 zinc solid plus 2 H3PO4 aqueous leads to 3 H2 gas plus zinc phosphate. Okay, and now we have a fully balanced chemical equation. Any questions on this example? Okay, let's continue on with our problem solving. So I'd like you to try to balance the following chemical equation, and any method can be used. So let's spend about 3 minutes on this problem, and we'll discuss this example in about 3 minutes. Again, don't be shy to message your responses in the chat as a public or private message, or don't be shy to unmute and share your responses verbally or ask questions verbally or in the chat. So we'll discuss this example in about 3 minutes. And we already have some responses for this example. It's pretty fast. Let's try to get a few more responses in the chat, and we'll discuss in about another 2 minutes. And the responses I see in the chat look good so far. Let's try to get a few more responses so I'm confident that the class is comfortable with this balancing equations material. And we'll discuss momentarily. And we'll discuss this example momentarily in about a minute to 30 seconds. Let's try to get a few more responses in the chat, just so that way I can provide feedback to as many students as possible. Okay, so let's discuss this example. So we have 2 nitrogens on the left and 2 hydrogens on the left, and we have 2 nitrogens and 4 hydrogens on the right. So we're going to play a little guessing game now. 2 times what is equal to 4 hydrogens? So what coefficient do we need for hydrogen? What coefficient do we need for hydrogen? 2, yep, perfect. So now we have our balanced chemical equation and all is right with the world. Okay, so let's keep going and let's do a few more examples. So let's look at the following chemical equation, and I'd like you to spend about 3 minutes trying to balance the following chemical equation. And we'll discuss this example in about 3 minutes. In the meantime, I'd like to see a few responses or questions in the chat. And really don't be shy to share in the chat or unmute and share your responses verbally. And we'll discuss this example in about 2 minutes. Let's try to get a few more responses in the chat. And if you have any questions at all balancing these equations, or if you'd like me to provide feedback for your solution, don't be shy to message me in the chat or state your responses verbally. And the responses that I have received in the chat so far look good. Okay, so I see a lot of reasonable responses in the chat. So let's discuss this example. So we have 1 calcium and 2 chlorine atoms in calcium chloride. We have 1 silver, 1 nitrogen, and 3 oxygen atoms in silver nitrate. We have 1 silver and 1 chlorine atom in silver chloride. In calcium 2+, we just have 1 calcium atom. And in nitrate, we have 1 nitrogen and 3 oxygens. Okay, so let's start by balancing any of our elements that are not balanced. So as we see, chlorine is clearly not balanced. So let's play a guessing game. 1 times what would give us 2 chlorines? What coefficient should we guess? What coefficient should we guess for silver chloride? 1 times what gives us 2?
Two.
2, yep. So as a result, we have 2 silver and 2 chlorine. Okay, now silver's not balanced, so we play another guessing game. For silver nitrate, 1 times what would give us 2 silvers? Again, it would be 2. And as a result, now we have 2 nitrogens and 6 oxygens. Now, nitrogen's not balanced, so 1 times what would give us 2 nitrogens? Again, we put 2. So that gives us 2 nitrogens and 6 oxygens. Okay, so now we'll rewrite our balanced chemical equation that we've verified has the same number of atoms of each element on each side of the chemical equation. Okay, so here's our balanced chemical equation, and we're complete from this problem. Any questions on this example? Any questions on this example? Okay, so let's try and let's work on another balancing chemical equations example. This is another combustion example, and this one's a little bit tricky. So let's spend about another 3 minutes trying to balance the following equation. I just really want to make sure we're comfortable balancing equations, because if you don't have a balanced equation, the next few topics in this chapter will be quite difficult. So we'll discuss this example in about 3 minutes. And again, don't be shy, and thank you again for sharing your responses in the chat. It's really helpful for me to provide feedback and get a sense of how the class is doing on these problems. And the response that I received in the chat quite quickly for this example looks perfect so far. But don't be shy to take your time, and we'll discuss in about another 2 minutes to 2.5 minutes. Let's try to get a few more responses in the chat, or at least a few more questions if you're having any difficulty or any questions about these problems. And the responses I see so far in the chat look good. They're perfectly correct. And we'll discuss in about another minute. Okay, so let's discuss this example. So in this case, let's first make a tally of the atoms of each element. So we have 1 nitrogen and 3 hydrogen. We have 2 oxygen atoms. On the right-hand side, we have 1 nitrogen and 1 oxygen in nitrogen monoxide, and 2 hydrogens and 1 oxygen in water. So let's first start by balancing. Let's first start by balancing our non-pure element species. So let's leave oxygen alone for now, and let's balance something that's not oxygen. So in this case, it's best to start with hydrogen. We have 3 hydrogens on the left. We have 2 hydrogens on the right. So this is a great opportunity to use the least common multiple method. So what we're going to do is we're going to multiply our coefficient for ammonia by 2 to give us 2 nitrogen and 6 hydrogen. We're going to multiply our coefficient for water by 3 to give us 6 hydrogen and 3 oxygen. Okay, so now if we add up our total number of oxygen atoms, we have 4 oxygen atoms on the left. Sorry, 4 oxygen atoms on the right. Now we want 4 oxygen atoms on the left, so 2 oxygens times what would give us 4 oxygens? 2 times what would give us 4? So before we actually try to balance oxygen, we should balance nitrogen next. So you notice how we have 2 nitrogens now on the left? We have to adjust this calculation a little bit because we still have to balance nitrogen. So if we have 2 nitrogens on the left, we need a coefficient of 2 to give us 2 nitrogens and 2 oxygens. Now, when we add up and calculate our total number of oxygens, we get 5 oxygens. Now this is important because if we have 2 oxygens on the left, 2 oxygens times what would give us the needed 5 oxygens? So 2 oxygens times what coefficient would give us 5 oxygens? What fraction or what coefficient would we need to guess? Well, the trick is we put what we want on top, what we have on the bottom, and that gives us 5/2. So now rewriting our balanced equation. So rewriting our balanced equation now, we have 2 ammonia plus 5/2 oxygen gas leads to 2 nitrogen monoxide plus 3 H2O. So again, half notation is showing its strength in balancing an equation that contains an isolated pure element such as oxygen. Half notation is super helpful when you're dealing with combustion reactions. So now this isn't our final balanced equation. So we need to adjust our coefficients so that we don't have any fractions. So what do we multiply all of our coefficients by to get whole numbers? What do we multiply all of our coefficients by? We multiply them by 2. And that in turn gives us the following balanced equation. We have 4 ammonia plus 5 O2 gas leads to 4 nitrogen monoxide gas plus 6 H2O liquid. And now this is our complete balanced equation, and we're finished with this problem. Any questions on this example? Any questions on this example? Okay, so let's keep going now. And let's try to balance the following chemical equation using any method. Let's take another 3 minutes to work through this problem, and then we'll discuss this example together as a group. Again, don't be shy to submit your responses via Canvas chat or to communicate your responses verbally via the Zoom chat. And we'll discuss in about 3 minutes. And the responses that I'm seeing in the chat so far for the balanced coefficients look perfect so far. And we'll discuss this example in another 2 minutes. Okay, so let's now discuss this example, and thank you again for sharing your responses in the chat. So again, as always, we're gonna count the number of atoms of each element. So we have 2 aluminums, 3 carbons, and 9 oxygens in our reactants. We have 2 aluminums and 3 oxygens in aluminum oxide, and we have 1 carbon and 2 oxygens in carbon dioxide. We're gonna leave oxygen alone for now. Again, we always balance the elements found in the least number of compounds. So my question to you is, to balance carbon, 1 times what would give us 3 carbons? 1 times what would give us 3? 1 times what would give us 3? 3, yep. So that gives us 3 carbons and 6 oxygens, which if we check and add them up, we have 9 oxygens total in addition to 2 aluminums and 3 carbons, which matches the 2 aluminum, 3 carbons, and 9 oxygens on the left. So everything's good to go. We have a completely balanced equation, and that's it for this problem. Now, really to showcase how half notation can make your life easier, if we don't have any other questions on this example, the responses I got were perfect so far. Let's now look at the following problem, and I would highly recommend that you use half notation. It will save you a lot of time on this problem in particular. So let's spend about another 2 to 3 minutes on this problem, and then we'll discuss together as a group. And we'll discuss in about 2 to 3 minutes. And the responses I see in the chat look great so far. Again, half notation is really pulling its weight on these sorts of problems. So we'll discuss in about another 1.5 to 2 minutes. Let's try to get a few more responses in the chat and then we'll discuss. Okay, so let's discuss this example. So we have 1 aluminum and 8 sulfurs on the left. We have 2 aluminums and 3 sulfurs on the right. So let's focus now on adjusting our coefficients and balancing. Let's balance aluminum first. Sulfur, you can also choose to balance sulfur first, but I find really there's no difference in which one you choose, but let's arbitrarily balance aluminum first. So if we have 1 aluminum on the left, 1 times what would give us 2 aluminums? What coefficient do we guess? 1 times what would give us 2? 2, yep. Okay, and now things are going to get a little bit interesting. We have 8 sulfurs on the left. 8 times what would give us 3 sulfurs on the right? 8 times what would give us 3? What coefficient do we guess for sulfur? 3/8. Yeah, you can also use the least common multiple method. That also works. There's nothing wrong with either method. I just personally like half notation when it's useful, when you have an isolated pure element. So now what we're going to do is we're going to rewrite our equation, and then we're going to convert this fractional equation into a real, legitimate balanced equation. I mean, we can't have fractional coefficients. There's no such thing as half a molecule or a fraction of a molecule. That doesn't have any physical interpretable meaning. Okay, so let's try to find a whole number. Let's try to find a whole number coefficient that we can multiply all of our reaction coefficients by in order to give a whole number. Since we have an 8 on the bottom in our denominator, what should we multiply each of our coefficients by? What should we multiply each of our coefficients by? 8. And that in turn gives us 16 aluminum solid plus 3 S8 solid plus 8 aluminum sulfide. There we go. Any questions on this example? Any questions on this example so far? Let's continue practicing balancing chemical equations. I really want to make sure everyone's comfortable with this material. So let's balance another type of chemical reaction. This is a typical acid-base reaction. So I'd like you to take a moment and try to balance the following chemical equation using any method you prefer. And I would highly recommend for acid-base and exchange reactions to think about balancing in terms of ions rather than individual atoms. So we'll discuss this example in about 3 minutes. And again, don't hesitate to submit your proposed responses via the Canvas chat or ask any questions verbally or via the Canvas chat. And when we discuss, I'll show you a nice trick for balancing these sorts of problems. These specific reactions known as acid-base reactions. And the coefficients I see submitted in the chat so far look perfect. And the coefficients that I see so far look perfect. Okay, so let's discuss this example. And when you think about acid-base reactions, our acid has H plus and our base has OH minus. Now this is important because a critical foundational idea in acid-base reactions is that H plus OH minus leads to water. So you want to have equal numbers of H plus and OH minus in your balanced equation. So looking at phosphoric acid, we can think of phosphoric acid as having 3H plus, 1 phosphorus, and 4 oxygens. Barium hydroxide has 1 barium atom, 2 oxygens, and 2 hydrogens that I'll write as 2 OH minus. Now, if I want equal numbers of H plus and OH minus, I can use the least common multiple method for my reactant side. So I'm going to multiply my number of high H plus atoms by 2 to give us 6 H plus, 2 phosphorus, and 8 oxygens. I'm going to multiply my number of hydroxides by 3 to give us 3 bariums, 6 oxygens, and 6 hydrogens. Okay. Continuing on, looking at barium phosphate, we see that we have 3 bariums, 2 phosphorus, and 8 oxygens. So we've balanced it using this acid-base shortcut. And then for water, looking at water, which is H2O, the number of H plus atoms and the number of water molecules must be identical. So then if we have 6 H plus, we're going to take our 2 hydrogens and 1 oxygen found in water, and we're going to multiply it by 6, giving us 12 hydrogens and 6 oxygens total. And as we notice, if we add up our hydrogens, we have 12 hydrogens, 6 oxygens from our H plus and OH minus. Just to make sure that everything is truly balanced, let's write in our coefficients and count the total number of atoms of each element. So we have 2 H3PO4 plus 3 barium hydroxide leads to barium phosphate plus 6 H2O. Does this shortcut make sense? Does the logic behind this shortcut make sense? For acid-base reactions, you want equal amounts of H plus and OH minus. And if you use the least common multiple method to figure out the smallest common amount of H plus and OH minus, you can very quickly balance these kinds of acid-base reactions. Did that make sense to everyone? Does that make sense to everyone so far? Okay, let's look at another example. This is another type of acid-base reaction, but it follows slightly different rules. I would recommend balancing this equation using your standard method. So let's take a look at the following reaction and let's try to balance it. and we'll spend about 3 minutes on this problem. I know we're doing a lot of practice, but if you can't balance a chemical equation, the remainder of this class is going to be quite tricky. So I really want to make sure we have this fundamental skill established. And we'll discuss this example in about 2 to 3 minutes. And let's try to get a few more responses in the chat before we discuss. And let's try to get a few more proposed responses in the chat, and then we'll discuss. And the responses I see in the chat look good so far. Let's try to get at least another 1 to 2 responses in the chat, and then we'll discuss. This is a combination of an acid-base reaction and a decomposition reaction for those who are curious. We've actually performed a reaction similar to this in the laboratory, though not with lead, of course, because it's toxic. So let's spend another minute on this example, and then we'll discuss. Okay, so let's discuss this example. So in hydrochloric acid, we have 1 hydrogen and 1 chlorine atom. In lead carbonate, we have 1 lead 2 carbons and 6 oxygen atoms. In water, we have 2 hydrogens and 1 oxygen. In carbon dioxide, we have 1 carbon and 2 oxygens. In lead chloride, we have 1 lead and 4 chlorines. Okay, so really we have a lot of choice in terms of what we want to balance first. Let's try to balance the elements found in the least number of compounds first. So let's start with chlorine. So what times 1 would give us 4 chlorines? What times 1 would give us 4 chlorines? 4, okay? So a coefficient of 4 gives us 4 hydrogens. So then what times 2 would give us 4 hydrogens? What times 2? What coefficient do we guess for water? 2, exactly right. So now we have 4 hydrogens and 2 oxygens. So in total, let's leave oxygen alone for now. And looking at carbon, we have 2 carbons on the left. So what times 1 would give us 2 carbons? What coefficient do we guess for carbon? 2, yep. So that gives us 2 carbons and 4 oxygens. Added together, we have 6 oxygens, 2 carbons, 4 hydrogens, and 1 lead. On the left, we have 4 hydrogens and also 4 chlorines. 4 chlorines, 1 lead, 2 carbon, and 6 oxygens. So this equation is balanced. Let's just write down our balanced chemical equation now. So we have 4HCl aqueous plus lead carbonate leads to 2H2O plus 2CO2 plus lead chloride, which is PbCl4. Okay, so we've completely balanced this equation. And we're all set with this problem. Any questions on this example? Okay, so that's a good stopping point for today's supplemental lab lecture. We'll continue lecture tomorrow. We're then now going to switch gears and talk a little bit about the calculations for today's and yesterday's laboratory.